You ever pop open one of your gadgets and just stare at the little city inside? It's not just code and magic, you know? There's a real art to it, a physical craft that literally brings our entire digital world to life. So today, let's get our hands dirty and dive into how it's all made. So, what's the secret sauce? What does it actually take to turn that little pile of components and a blank board into a working circuit? Well, it's a journey, for sure. It's going to take some precision, the right tools, and a deep respect for an invisible force that can kill your project before you even begin. Every artist needs their brushes, right? Well, for us, our toolkit starts with a few key hand tools. Let's gear up and look at the absolute must-haves you'll need to get started. First up, the good old wire cutter. It looks simple, but it's absolutely crucial. Its whole job is to make clean, precise snips on wires and component legs. Trust me, getting a nice clean cut, especially when you're working in a tight space, makes all the difference. Next, we've got the long nose pliers. Just think of these as your super precise fingertips. They're perfect for grabbing those tiny little components, holding things steady while you work, and bending the leads just right so they slot perfectly onto the circuit board. And rounding out our top three, the wire stripper. Look, you could try to strip a wire with a knife or your cutters, but you're probably going to nick the delicate copper strands inside. This tool, though, it's made for one job, to take off that outer plastic insulation perfectly every single time with zero damage. Okay, so you've got your tools, you're ready to start building something amazing. But hold on, there is a hidden danger lurking around you, an invisible killer that can destroy your most sensitive components before you even get a chance to power them on. You know that little zap you get sometimes? Like you walk across a carpet, reach for a doorknob, and zap! That's static electricity. And while for us, it's just a little surprising, for an electronic component, it is a full-blown catastrophe. Now get this, for you to even feel that tiny shock, your body has to build up a charge of about 3,500 volts. Sounds like a ton, right? Okay, keep that number in your head for a second. Because a sensitive microchip, a transistor, it can be permanently fried by as little as 50 volts. 50. That means you can literally destroy your parts without ever feeling a thing. The damage is done, and you'd never even know it. This whole phenomenon has a name, electrostatic discharge, or ESD. It happens from the simplest things, walking on a rug, pulling off a fleece jacket. That friction builds up a charge on your body. And when you touch a component, your body instantly tries to equalize that charge, sending a sudden, violent jolt of electricity that can blow microscopic holes right through its delicate internal structure. It's a huge, huge problem in the electronics industry. So if this invisible enemy is basically everywhere, all the time, how in the world do you fight it? Well, thankfully, there's a whole science to creating ESD-safe environments, and we've gotten pretty good at building up our defenses. The first line of defense is just knowing what you're dealing with. You'll see the symbol, the triangle with the hand getting zapped, on any parts that are sensitive to static. It's a universal warning. And you'll often see it on special anti-static packaging in tape that basically screams, hey, handle with care. In a pro setting, they take this stuff very seriously. A proper ESD-safe workstation will have special conductive mats on the floor and the bench, all of them wired to a common ground point. But here's the key. The person doing the work also has to be grounded, usually with a wrist strap. They'll even use a little tester like this one to make absolutely sure they have a solid connection to ground before they touch a single component. And the gear goes on and on. We're talking conductive storage boxes, special shielding bags that act like a little Faraday cage around your parts, even anti-static finger cots, shoes, and floor mats. The whole goal is simple. Make sure that you, your workbench, and your components are all at the exact same electrical potential. No difference in potential, no sudden discharge, no problem. All right, our parts are safe from the invisible killer. Now it's time for the real fun, the real art, making the connections permanent. And we do that by soldering, literally forging electrical bonds with molten metal. And this is our main tool for the job, the soldering iron. The best way to think about it is like a superheated pen, but instead of laying down ink, it uses intense heat to draw connections with metal, writing the physical language of a circuit. It's actually a pretty simple device when you break it down. You've got the plug, which gets power to the heating element inside. That element gets crazy hot, and it funnels all that heat down to the metal tip. That's the business end that actually melts the solder. And of course, the insulated handle is there to, keep you from burning yourself. Now, the ink for our pen is the solder itself, which is a metal alloy. You can see there are different recipes for different jobs. For electronics, the classic, the go-to, has always been this 60-40 mix of tin and lead. It has a nice low melting point and flows beautifully. It is worth pointing out that most of the industry has moved to lead-free solder now, which is better for the environment but can be a little trickier to work with.
So you've got the iron, you've got the solder, but honestly, that's the easy part. The technique is everything. A good solder joint is strong, reliable, and will last forever. A bad one? Well, that can cause you headaches and frustrating problems that are an absolute nightmare to track down.
Okay, so here is the secret. It's all about this four-step dance. Number one, you use the iron to heat the things you want to join, the component leg and the copper pad on the board. Get them both hot. Then, you touch the solder wire to that heated connection, not to the iron itself. The heat from the parts melts the solder, letting it flow over everything and create a perfect bond. Then, you just pull the solder away, pull the iron away, and let it cool down on its own. And here's what we're aiming for. On the left, that's a picture-perfect joint. It's shiny. It forms this nice little concave volcano shape, and it's flowed evenly over both surfaces. But on the right, that's a cold joint. This is what happens when you don't use enough heat. The solder just kind of balls up into a dull, lumpy blob. It's a terrible electrical connection, and it's super unreliable. Another classic mistake is just going overboard with the solder. See how the good joint on the left uses just enough to form that solid connection? The one on the right is a giant blob. Not only does it look messy, it's actually dangerous. A blob that big could easily flow over and touch the connection next to it, creating a short circuit and making the whole thing fail. So we've got our tools, we've got our safety plan, and we know the technique for making a perfect connection. But where does all this happen? What is the final canvas where we paint our electronic masterpiece? It all comes together right here on the printed circuit board, or PCB. This is the stage. Every single component is carefully placed and soldered onto these little copper pads, and those pads are all connected by these thin copper pathways called traces. The traces are the wires, all neatly laid out for us. From the simplest little hobby kit to the motherboard in your computer, it all comes down to these fundamental skills: handling parts safely, protecting them from ESD, and soldering them carefully onto a PCB. So the next time you see a circuit board, just think, isn't it incredible that from these few, simple, careful steps, the entire complexity of our modern digital world is built?